there were several questions about the content that are a nice way to lead into the rest of the lecture. So someone said, I'm just going to read it out. I'm not really sure how practical this all is. This all seems very expensive to do, where this all is what we're going to discuss today as well, Laplace approximations for deep learning. Why do we need to do these 4 steps? Why not 5 or 3 or something else? Then there's a question where someone, I think this is good to recap, because maybe what I said wasn't entirely clear. Someone said, I claimed that when you're training a deep neural network with new data, then the model tends to forget the old data. Isn't that also a problem when we do hyperparameter training? So that's not what I said. I said if you're adding data to a Gaussian process posterior, then that's a very well-formed operation. In fact, it's a closure from the computational perspective. You just add data and you get back a data structure that is of the same form as the prior, but conditioned on the observations. And that ensures that the model does not forget existing data. In fact, if you have redundant data, so if you, in the extreme case, have 2 observations at the same point in a Gaussian process, then the model will produce a posterior that is a weighted average of those observations, weighted by their relative precisions in the observations. And so that's exactly, I would say, the correct functionality you would look for if you have several conflicting observations. The hyperparameter training actually has nothing to do with that. You can do hyperparameter training on a given data set. Of course, if you look at some data set, then train for hyperparameter maximum likelihood estimation, and then keep the hyperparameters fixed and add more data to the model, then those new data are not going to be reflected in the choices of the hyperparameters, but you could still continue to optimize the hyperparameters as you go, and nothing would break. So it all just works for Gaussian process models. I didn't understand how you approximate the Hessian. I understand why, because it's a bit tricky, and we would need to talk a lot more about automatic differentiation. I'll do that a little bit today, but there is a fundamental limit to how much of that we can do in a lecture like this. And what happens if the network is highly nonlinear in the parameters? So that's a point that I'll raise again today. The model, the approach that I'm constructing is fundamentally an approximate one. It uses a linearization at the train point. That means it's potentially wrong, but it's also lightweight. And there are alternatives out there that I'll briefly mention in passing that have a higher quality in the approximation of the posterior, but also correspondingly higher computational cost. And if you compare this criticism, like, oh, but this is a bad approximation, basically, to basically this criticism, which is sort of between the lines, oh, but this can be very expensive. Why are you doing something this expensive? Then you see exactly the kind of tension that research in probabilistic deep learning is currently under. So there's, on the one hand, people who come from, let's say, the practical deep learning perspective, who say, but I'm already using all the resources I have to train the model. Why do I need to do something else to quantify uncertainty? And on the other hand, I don't know, rigorous orthodox people who say you're only allowed to be Bayesian if you're going to be correctly Bayesian. And no matter what it costs, let's do the most expensive thing. So to remind you what we did on last Thursday, I claimed that every deep neural network is secretly a Gaussian process. You just haven't realized yet. And what I mean by that a little bit more precisely is that if you think of the trained neural network as a maximum a posteriori estimate, then it is in a very precise sense that I outlined on Thursday a 0th order approximation to the correct posterior. It just finds the mode. And this Gaussian process that I highlighted is the 2nd order approximation to that posterior. So it's better than the 0th order approximation, but it's still an approximation. You might want to think about higher order terms, 3rd, 4th, 5th, whatever order, or some other basis to project into that might lead to a better quantification of uncertainty. But for us here today, it's more about thinking about even adding a probability measure to this, to a trained deep neural network than about how to do this precisely. So how do we construct this posterior? Well, we do these 4 steps effectively, which you can also think of computationally as 3. The first one is you train your deep neural network in whichever way you like, just as you did before. That gives you a point estimate. That's the blue thing. That's the trained neural network. That trained neural network is a function, a nonlinear function of inputs that you get by fixing the parameters of the network to a particular value, such that the gradient on a training loss is close to 0. Then there's a second step, which is only conceptual. We're imagining our neural network as a local linear function in parameter space. That's not actually a computation. It just tells us which quantity to look out for, namely the Jacobian of the network, with respect to its parameters, evaluated at the trained parameters. Then there is a second computational step, which is to construct the curvature of the loss function in parameter space at the trained points. Actually, this should be probably theta star here. And we already noticed, and we'll discuss this more today, that here I think of this more as a sort of a symbolic representation of some curvature operator. So if you, of course, from Taylor's theorem, it would ideally be the Hessian of the loss function. But in general, the Hessian is going to be intractable. So one first simplification would be to assume that, or like leverage this assumption that the network is piecewise linear, no, not piecewise, locally linear in its parameters. And then this curvature matrix becomes this, well, imposing expression, the generalized Gauss-Newton, which is an outer product of Jacobians evaluated at the Hessian of the loss in terms of its logits, not in terms of the parameters, plus a regularizer, which is easy to evaluate. And so that's a computation that involves going through the whole training data set. So there's a sum here that goes through the training data set. And that means we have to reflect on what the network has actually learned from the data. This is also an operative part. If you're not doing that, then there is no effect, there is no way to quantify how much information the training data provide. But we can think about how we can speed up this computation through further approximations. And then there's a final step, which is again just a conceptual one, namely to realize that if we think of this curvature matrix as providing an approximate posterior covariance on the parameters and the neural network as a linear function in the parameters, then the associated posterior probability measure on the function represented by this neural network is a Gaussian process with a mean function given by the trained neural network and a kernel given by this so-called Laplace tangent kernel, which is the inner product between the Jacobians weighted by the inverse of the curvature of the loss at at the point in the parameter space where the trained neural network lies. By the way, some of you may have heard, who has heard about the tangent, the neural tangent kernel? A few people have heard this is sort of a buzzword from theoretical analysis of deep neural networks. If you've done statistical learning theory, did Matthias Hein do this? No. So advanced statistical learning theory for deep neural networks that you might get in some more specialist lectures, like the one by Antonio Orvieto, might point out that there is a nice way of theoretically analyzing the capacity of deep neural networks and their asymptotic training behavior in terms of this object, which is called the neural tangent kernel. So that's just the inner product between the Jacobians. Funnily enough, the original paper that introduces this object doesn't explain why this is a tangent kernel. They just use the word, and they never explain what this has to do with any manifold and tangents on that manifold. They just use the word. But you can think about this object from this perspective as the prior of this, the associated Gaussian process prior of this neural network without considering the data. So the neural tangent kernel, if you want to have sort of a mental note for this object, is the prior Gaussian process prior covariance of a deep neural network. and this Laplace tangent kernel is the associated posterior kernel. Here's another variant of the plot that I showed you on Thursday that highlights what the effect of this kind of these extra computations is. On the left, you see, again, this 2 moons data set with a classifier, a ReLU classifier trained on this training data set. And this is the maximum a posteriori estimate. So for this, I trained a neural network. Then I take the trained network and just push the logits through a softmax, or a logistic in this case, because it's binary. And what you can see is that while this network has learned to classify the training set correctly, it's arguably massively overconfident in its predictions as we move away from the training data. For example, if you think about the decision boundary, that this is the white line here, this is extremely narrow, right? So this network claims that you can perfectly separate this belongs to the red class and this belongs to the green class, which seems like not, maybe not really a conclusion that you can draw from this particular training data set, right? I hope you agree with me on this. While if you use this Laplace tangent kernel, you get this kind of prediction, which is, well, arguably better. I mean, it's just a picture, so we can discuss how good of an approximation it is. But you can see that this network has a lot more structure, and in particular, that is much less confident about its predictions. For example, this region over here, which is maybe arguably sort of an artifact of the training. There's just one ReLU that's lying around there, or a set of ReLUs that is just sort of sitting here and doesn't have a gradient because there are no training data, now actually is associated with very high uncertainty. Why? Because there is no corresponding precision term in the generalized Gauss-Newton, and so it gets associated with a large uncertainty, and the model just doesn't know what the value is there. So that's the recap of the ideas from Thursday. Now what I'd like to do today is to answer maybe the first question that was raised in the feedback, namely, well, what is this all good for? Why would I care about probabilistic functionality in deep learning? And here, so first of all, I'd like to say that I'm today going to maybe move a bit more like in a research talk than in a lecture. So I'm just going to highlight a bunch of results that are all pretty recent from the last few years, that from a stream of research that basically highlights the value of this probabilistic functionality for deep learning. That's going to be relatively fast, and I'm going to be sometimes a bit superficial. I won't always explain exactly how these methods work, just give some ideas, some highlights, because otherwise we can't go through the whole list. And also, in terms of the content, I really just want to provide some arguments for, well, being probabilistic about deep learning that are also more generally just arguments for probabilistic reasoning in machine learning. So it's effectively a continuation of lecture 1, if you like. Why do you want to be uncertain? Well, because uncertainty endows downstream functionality. Just having error bars in itself is nice and all. You can make a nice picture like this, but it doesn't really, immediately have value. But there are tangible functionalities that you want from a usable learning machine that require uncertainty as sort of for their internal computations. And let me see if I can convince you of that. So maybe the first step is an answer to the immediate sort of concern you might have, which was basically, I guess, the first feedback. So I'm still holding out to see if that's actually useful. So a first question that I also tend to get in research talks is, Hessian, well, this is huge, right? So if my network has a large number of parameters d, then this curvature of the loss in the parameter space is of size d by d, and you need to invert it. So inverting a matrix is cubic in the size of the matrix, so it's d cubed. That doesn't scale. If you have large foundation models where d is, I don't know, a few billion, then I'm never going to be able to actually build this matrix. So the answer to this is twofold. So first of all, we'll still trying to be as close as possible to what people are currently doing in deep learning. So if your mindset is existing contemporary deep neural networks are missing functionality, like they don't have add buttons and they don't have delete buttons, they don't have enter and delete basically, right? Add more data, remove data, or something else. And you want to add some functionality to that, then this is probably the best point to start. Because we're beginning with the trained neural network, the network that everyone's already using. So if you're thinking of, I don't know, ChatGPT, then this is ChatGPT, right? And it's the original model. There is no extra thing to do, no extra computation to get to this point, which is a difference to other probabilistic approaches to deep learning, like ensembles or various sampling methods that, by the way, I'll talk about from Thursday onwards, which actually change the predictions, the mean predictions of the network. This one actually just keeps them the same. And then secondly, yes, this extra quantity, this red quantity, this curvature, will cost us something extra. It requires, at least on paper, a pass through the data set as one sum over all the training points, and then a computation of the backprop pass on that entire data set. So this phi is the quantities that you also need for backprop, for training. So that's like one extra epoch of training at the end to just construct the terms in the sum. And then you have to actually store them, so that gives you some extra overhead. And you then have to do some numerical linear algebra to find an inverse of this matrix. However, remember that numerical linear algebra is really the most efficient thing we have, and computing these gradients, these Jacobians, we can do with autodiff, which is another extremely powerful tool. So these computations, while they are not for free, involve maybe the most powerful computational tools available. They're massively parallel, they're shardable, they use automatic differentiation, which has bounded complexity. And then to find an inverse of that matrix, of course, we don't necessarily have to find the actual inverse, which is cubically expensive. We might use some smart approximate methods, like some of those that you encountered in lecture 3 or 4 when I first talked about probabilistic linear algebra with Gaussians. So you could, for example, by the way, one nice first observations might be that the multiplication with objects like this, with the Jacobians, can actually be done very efficiently in autodiff frameworks. So you can check in JAX, there is a functionality called a JVP, a Jacobian vector product. So multiplying a vector with this object doesn't actually have to be done by instantiating the Jacobian, instantiating the vector, and then doing an inner product. But instead, you can directly compute the projection of the Jacobian onto a vector using automatic differentiation functionality. So that might already speed up certain things. Also, this sum, you might be able to subsample, and you might not need to actually instantiate the objects in here either. These are typically closed form expressions because they're Hessians of the loss function with respect to the logits. Remember that our loss functions are typically exponential families. So their their Hessians tend to be explicit expressions that can be very efficiently computed. They're often diagonal matrices, so again, things can speed up. Overall, you should think of this object not as one monolithic specific matrix that has to be built and then kept in memory, but as an operator that offers a lot of opportunities to speed up computations approximately. And there's now increasingly software stacks to do that. So for example, there is a library that was recently highlighted at, I think it's at ICML, or it is going to be highlighted at ICML next week. Is it next week? 2 weeks from now? Whenever. In Vancouver, called Curve Linops by various people from across the world that provides additional or sort of encapsulated access to, for example, multiplications with this object or efficient approximations thereof, even for large models. And I'm going to show you in a moment examples where it turns out that depending on what you actually want from your probabilistic functionality, you can sometimes get away with removing a lot of structure here, even with ignoring all the structure and just treating it as a diagonal matrix with just a scalar constant in front. And then obviously multiplication is super easy. When you do that, you lose something as well, but for certain types of functionality, it's actually enough. The other question that usually then comes up is sort of the opposite thing. So once I've argued that curvature is maybe something we want to invest in because it's just about tractable, someone else then says, oh, but if you do that, that's way too simplistic. You should be doing something much smarter, like estimating the true posterior. For example, using a Markov chain Monte Carlo method. What that is, we'll talk about next Tuesday. So build samples, basically, from the posterior. And here, my argument is, if you want to do that, you're absolutely invited to do that. So if you're the kind of person who doesn't like a Laplace approximation as a simplistic posterior, and you want to have a stronger sense of quantifying uncertainty, nobody is keeping you from using computational resources to build a better posterior. Well, when you do that, you typically tend to encounter a quite high computational cost. So I already mentioned on Thursday, one alternative to a Laplace approximation is called an ensemble. You just train a fixed collection of deep neural networks. Instead of training one, you train 20. And then you have to keep around 20 trained neural networks. And whatever you do with them, you just have to just multiply by 20 and do on all of them. That can be good for certain applications. It's, for example, the standard approach in climate science. You just have 20 different models that you train. And then you can compare between them. If you really want to be, like, in some sense, confident that you have completely separate predictions, then that's a good idea. But that also means you have to keep around 20 models. And that's probably not going to happen for foundation models. It also means you then have effectively a model that has 20 degrees of freedom to quantify its uncertainty. So if you think of the covariance between these models, it's a rank 20 object. And it's fundamentally limited to those 20 dimensions, which is different to this framework, where you can basically choose the degrees of freedom of the model. And depending on the application, ensembles might actually be worse than a linearized model. OK. That's my high-level argument for why you might still want to consider these approaches. Now let me show you some concrete examples of probabilistic functionality that you get using this framework. Any questions? No. OK. Maybe you didn't even need convincing. OK. So my very first argument is a very, very basic one, and it's a purely formal analytic one, where it turns out that just having a posterior measure on a neural network, so being probabilistic about deep learning, already fixes some problems, no matter what the posterior is. So even the most naive, idiotic posterior you could come up with that costs nothing already fixes some problems. And here's the formal argument for why. So there was a wonderful paper in 2019 at CVPR by a certain Matthias Hein, which he published actually before he came to Tübingen. He just wrote it and then sent it in, which shows through a formal analysis in a theorem that classification neural networks, so neural networks used for classification that use ReLU nonlinearities throughout, everywhere, are guaranteed to be asymptotically overconfident. And here's how this works. So consider again this empirical risk minimization problem that I've now already mentioned a few times. So we're finding our trained neural network, the parameters of this trained neural network, by minimizing this regularized empirical risk, which consists of like this loss, which is a regularized empirical risk. So it's a sum of individual terms, where each term depends on one pair of data, or one datum, and the neural network that depends on all the parameters. And now let's assume that our deep neural network is ReLU, a ReLU classifier. So that means this F has a particular structure. It's a hierarchical combination of linear layers and then a nonlinearity that is given by a ReLU. So I guess everyone knows what a ReLU is. Yeah? So ReLUs are piecewise linear functions. Right? So the ReLU is something like this, a maximum between 0 and x. But it's not in a one-dimensional space. It's in a higher dimensional space. Right? So we are predicting a multivariate output. So you can imagine your data set. I'm going to actually, over there's some data set, right? And in this input domain, in this two-dimensional plane for this picture, or in a higher dimensional plane for an arbitrary application, in X space, after training, you have a lot of VLUs lying around. And by a VLU, I mean something that has a point where the kink lies, and then a direction along which the function becomes linear. Right? So we can have a second one, and a third one, and a fourth one. And do you understand what I mean by these arrows? So every single one of these terms is one line where this thing turns from a 0 to a linear function. And then along this direction, it's a linear function. You following? Yeah? OK. So now if you have your training data set in here, now as we move away from the training data, let's say we find the centroid of the training data, and then we find a random direction. It doesn't matter which direction it is. And we move along this direction away from the training data, in any direction. Then eventually, we will cross the very last VLU, right? The very last kink in a VLU nonlinearity. And then after that, in this direction, so there is some kind of region of piecewise linear functions, which are VLUs. After this, we're eventually in a region where the function is just linear. So as we go further and further away, it's just a linear function. Now, if you do multi-class classification, it's not one linear function, but it's number of classes linear functions. Right? If you do 10-class classification, it's 10 outputs. And eventually, they're all linear in this direction. So in that direction, one of those, let's say 10 outputs, will just happen to have the largest gain. Right? Because they're all linear. Each of them has a gain. With probability 1, one of them is the largest one. So as you now go further away and push these linear functions through a softmax, that one that is the largest one will just be arbitrarily far away from all the other ones if you go just sufficiently far away. And therefore, if you push it through the softmax, it'll basically be given probability 1. Does that make sense? So if I move really far away from the training data, my model will predict one particular class with confidence 100%. Well, arbitrarily close to 100%. That's what Matthias Hein is arguing in this paper. Here's the statement for this, now written as an actual sort of statement. But you can also see it in this picture. So here, what I'm plotting is confidence in one of the classes. It's obviously a different class in each region. So here it's the green class, there is the white class, here is the yellow class, and there is the, violet class or so. But it doesn't matter. One of them is always the most likely one. And then as you go further away, you'll always get 100% confidence, or effectively 100% confidence. So there was a follow-up paper by a PhD student, Agustinus Cristiadi, who is now a professor in Canada, and Matthias Hein and myself, where we observed that if you just replace this point estimate, this f of theta star, with this Laplace approximated Gaussian process that I mentioned, but actually it doesn't matter what the posterior covariance of this Gaussian process is, as long as it uses this tangent kernel with an arbitrary covariance inside, then this problem goes away. And it goes away not because of some like nice calibration or whatever, but just because a probability measure is a more meaningful object, fundamentally more meaningful than a point estimate. Or maybe the other way around, point estimates are just wrong, actually. So how does this work? Here's a sketch of the proof. So if we go far away from the training data, then asymptotically, our network is linear. Right? So there's a region in X space where as you go further and further away in X, you can think of the network as a linear function where the actual gain of the linear function depends on what the parameters is, but it doesn't matter, it's just some function. And now assume that we have put any arbitrary Gaussian belief over the parameters, where this posterior covariance might come from a Laplace approximation, but in fact it might even be the unit matrix, just something absolutely arbitrary. Then the corresponding Gaussian process measure on the function, which is now piecewise linear in these regions, is, well, we've already had, well, this notation is a bit different now. You can think of this as phi instead of j. You can think of phi. The important thing is that it contains a linear function in the prediction. And then in its kernel, this inner product between these two linear functions and the whatever the covariance on the parameters is. So it doesn't actually matter what's in here, whether this psi is some specific matrix or just a unit matrix, and what actually is in this A. It's just some matrix. So the variance grows clearly like x transpose something times x, like x squared. And if you're now using this simple approximation for what the expected value of the push forward of this logits through the nonlinearity is, then you'll find that your prediction far away from the training data is a sigmoid of something of order x divided by square root of 1 plus something of order x squared. So asymptotically, the 1 doesn't matter, and we're just dividing x by x, and it cancels out. And we asymptotically go to a constant. So the mental picture here is something like this. In logit space, down here, if you're just using a point estimate, this red curve, then yes, that red curve will keep growing as you move away from the training data, and it'll get arbitrarily large, and therefore its softmax will get arbitrarily close to 1. But the associated variance around it will also grow linearly with distance. And so the overall probability mass on one side of the 0 will asymptotically be a constant. And that's what this green line gives you, right? It just goes back to something finite. So if you just use a Laplace approximation and you don't even spend any compute on it, you just pretend you've done the computation, but you just set the covariance to 1, which costs nothing, then you get rid of one problem of deep learning. You're not asymptotically overconfident anymore. That paper was published in ICML, and it has the title, Being Bayesian, even just a little bit fixes problems in deep learning. Question? So you said you could use a different function, not VLOOS. Yes. Obviously, you can use some other nonlinearity, and you'll have another problem, right? So the VLOOS here, I mean, VLOOS are quite common choice. The argument, of course, is only about VLOOS. So it's not a theorem that fundamentally holds for other kind of nonlinearities. But if you think about what kind of nonlinearities people actually use, there's basically two classes, I would say, right? Or three, maybe. There are nonlinearities that go back to 0 as you go far away from the training data, like Gaussians. Those are basically not used anymore because they have problems in high-dimensional spaces, so they don't get used. Then there are nonlinearities that go to a constant, like tan h. They are used, and they don't have this problem, but they're not used for all applications. And then there are basically variants of VLOOS, which are asymptotically also linear, like ZLOOS and all these variants of it, and they will inherit the exact same problem. So anything that grows as approximately linear or asymptotically linear as you go far away from the point where the operative part of the nonlinearity is, will have this problem. And it's really a fundamental flaw of point estimates. Just pretending that you know gives this overconfidence, because it then goes through the softmax afterwards and doesn't capture the fact that you're uncertain. Now, this only fixes an asymptotic problem. So you could argue, well, OK, it doesn't cost anything, but it also only applies in the asymptotic limit. And also, it only bounds the confidence away from 1. Right? So instead of becoming 100% confident, the model will still become finitely confident in one class over all the other ones. Maybe it won't be at 100%. It'll be at, I don't know, 30% or 99% or whatever. It's just guaranteed to be away from 100%. So is this enough? Well, actually, so there was a follow-up paper to this, which I like even more, which is a really nice sort of intuitive story for that. If you like get the idea, I think tells a lot about problems with deep learning and its exact formulation, which are all about lack of uncertainty or not considering the right hypothesis class. So let's say we wanted to fix, so actually back then, Agustinus and Matthias Hein and I were sitting together discussing what to do about this problem, so how to make that line go back to 0, basically. Or actually, yeah, 0 for, 1/2 for the binary case, so maximum entropy, right, 50-50 for each class. Or for multi-class, we would want it to go to 1 over the number of classes, right, so that each class gets the same probability. How do we do that? And we did some drawing around on a blackboard and discovered that if you want that to happen, you need the variance of this associated Gaussian to grow superlinearly. So it has to grow faster than, the variance has to grow super quadratically. So the standard deviation has to grow superlinearly as we go away from the training data. And that's not something you can do with a Gaussian on the trained neural network. And at first we thought, we need some kind of little hack to fix things somehow. But then actually, I think we realized that this actually contains an interesting story. So if you think about why this problem arises, let me go back to this picture. Then it's because, actually I can switch this off for a second. It's because we have this finite training data set, but we also use a finite deep neural network. Right? So our network will have, 12 layers, each of them a certain width, and ReLU nonlinearities. And that means there's a finite number of piecewise linear polygons in here, and then after that, it's just a piecewise linear function. Now, what you'd actually like to say, I think, or one way to approach this problem is to say, well, you just haven't seen training data everywhere yet. You don't know what training data might show up over here. And what you really want to say is that I would like to have an unbounded number of ReLU nonlinearities floating around the space. There should be a non-parametric model with an infinite degree of freedom that has infinitely many features lying around, but typically I can't keep track of those, right? It's just not something I can computationally do, and that's why I use a parametric model, a deep neural network. But now imagine the following construction. For that, I'm actually going to show you a one-dimensional plot again. You could think, it's just a, let's say, a Gedanken experiment, right? So in our head, we could imagine that around our training data, which is always confined to a finite region, to a compact domain, right? We can always draw something, a circle around all the training data if you have finitely many training data. Then outside of that region, there is more and more ReLUs waiting for us. There's like an unbounded number, countably infinitely many of them. But they just happen to all point away from the training data. So they are all like of this type. Right? So they are 0 towards the training data and then only get 1 later on. And therefore, during training, their contribution is actually 0. We never see them. We don't need them for our computation. Right? So in my head, I'm thinking of infinitely many features around them that I never need for training because they're all outside of the training data. But I know that if I would get there later on, if someone later on asks me, what's your prediction very far away from the training data? I would say, well, there was the original training data, which did something non-trivial to my model. And then after that, there were 58 additional ReLUs that I haven't seen yet during training. So they're all where they were at initialization. And they all contribute to my uncertainty. They contribute nothing to the point prediction because they're at initialization. So on average, their value is 0. But they're there, and they contribute a growing amount of uncertainty to the prediction. It's like having a 0 mean function in a Gaussian process, but a non-trivial kernel that keeps growing. And now the only thing left to do is to say, I'm going to put these additional ReLU nonlinearities in a regular fashion around the training data. So instead of saying they are at some arbitrary random locations, they are actually on a regular grid pointing away from the training data in each dimension, each input dimension. And I'll make that grid regular, and then I increase their number towards infinity, and at the same time decrease their value towards 0. And that's a construction you've already seen when we did kernel regression. And we'll end up with this particular Gaussian process that is associated with infinitely many ReLU features. Do you remember? It's this integrated Brownian motion kernel, this one which contains a minimum of the distance to the origin cubed. That's the kernel that shows up in this construction. It comes from Grace-Waber, right? These cubic spline kernels, which make these kind of predictions. And if you remember, the cubic spline kernel had a marginal variance that grows cubically with distance, not linearly. And that's exactly what we need, something that grows faster than quadratically in distance. So we can actually set up a theorem that is in that paper, which was published in EURIPS 2021, as a follow-up to the original CBPR paper by Matthias Hein, and then this being Bayesian even just a bit paper in 2020, which says there is this extra kernel that you can add to your trained neural network at constant cost overhead. It's an absolutely minimal cost overhead, which has the effect that as you go arbitrarily far away from the training data, the asymptotic confidence of your prediction will become the maximum entropy value, namely each class gets assigned probability 1 over the number of classes. And doing that involves a very simple algorithm which works as follows. I'm gonna show you code in a moment, but I can tell you how it works. You give me a training data set, I train my deep neural network on it, whichever way I like. And maybe I also do a Laplace approximation, but I don't have to. Now I compute the centroid of this data set. So for that, I compute the mean of the data set and the covariance of the data set. You all know that that's possible to do in linear time, right? I just go through the data set once, I add up all the points to get a mean estimate. So it's constant memory overhead, linear time in the number of data points. And then I use this centroid as a scale for a distance measure from the data. And then as I just return a Gaussian process for my Laplace approximation that uses whatever posterior uncertainty I have on the trained neural network. It could be a scalar, it could be a full Laplace approximation. And then when it gets an input, it also, in addition, so with a plus, measures the distance to the training data points on the centroid, and just adds a term that is cubic in the distance. And then you are guaranteed that asymptotically you'll get flat confidence over all classes. So here's a picture for that. I'm going to show you the code in a second. Again, here's our data set. On the left is the point prediction, which is this by now, hopefully you agree with me that this is not a particularly convincing classification result. It looks nice where the training data are, but very bad far away from the training data. This is the posterior covariance you would get from a Laplace approximation on the trained neural network. We've already seen that on Thursday. But now if we add something that measures distance to the data, we get something that's much less confident as we move away from the data. And that changes the uncertain prediction. So here is what you get from the Laplace approximation, which you've now also already seen. It's already better than the point estimate because it has this extra uncertainty sort of in these directions. But then we get this extra term, and this is a bit difficult to see in this plot, but you can see that maybe that these colors are a bit weaker than the ones on the Laplace approximation. And in fact, I'm going to show you in the code there it's easier to see. If you move further away, this actually returns to a white, completely white canvas. So there is some direction around here where it's a bit more blue, and then just outside of the plot, it just goes back to 0. There's also a way, I mean, in the paper, there's a zoomed out version of this plot, basically. But let me show you the code. You can find on BDUP Jupyter Hub the corresponding code, which is the exact same code as the one we used last Thursday. So I'm not going to go through it again. It does all of the stuff, right? Builds a prior, loads the data set. I just literally copy-pasted it. Builds a model, trains it in a normal deep learning fashion in JAX. You get your point estimate. Then we do a Laplace approximation using this Laplace package, blah, blah, blah. Just as last week, it gives us these uncertain predictions. And here you see the plot with the expected prediction for the labels. And you see that there's some reasonably high confidence far away from the training data. And here's the extra bit. That's one line, one cell. We find the centroid of the data. In this case, we don't have to do that because this particular data set is already nicely centered. Then we define a function that measures distance from the origin of the data and define a kernel that is effectively this integrated Brownian motion. It's the same kernel that I used in the kernel lecture on cubic splines. And then just add that kernel here to our Gaussian or Gaussian process posterior on the network. That's it. And the cost overhead of that is trivial. So you can run this cell yourself. It costs nothing. I'm not going to run it again because I have to retrain the network and it takes forever. And here's the corresponding plot. So after that, it's just plotting. And now you can see, maybe in this plot where you see the lines a bit better, that there's a difference between the Laplace and this ReLU calibrated Gaussian process regression. Here you see that the confidence in each class actually still kind of first grows and then flattens off under Laplace. And under this like asymptotic confidence prediction, it actually starts dropping again. So here's a maximum, and then afterwards it just goes back down to 50-50 for each class. So why am I excited about this before the break? Not so much because it goes back to 50%, but because it highlights two like structural problems with deep learning. The first one is that if you do a point estimate, then you can fool yourself into actual predictions, even if they are probabilities, that are just patently wrong. Like if you go far away, you'll get 100% confidence in one class. And the fix for that is just to put a Gaussian around this prediction. And it doesn't even matter how quickly this Gaussian, what kind of numbers you have in there, as long as the corresponding variance grows in the correct way, the one that naturally arises from a linear approximation, then that problem goes away, this asymptotic overconfidence problem. And then secondly, deep neural networks are fundamentally parametric models, as we discovered in lecture 3, 4, 5, and 6, right, for regression. They are more fancy ways of learning a finite feature set, but they're still finite, which is fine for many applications, but in particular for asymptotic functionality, as you move what's called out of distribution, so away from the training data, for some kind of properties that you want the model to have, you have to sort of assume that there is an additional set of features that you just haven't encountered yet. So effectively a non-parametric model that you just haven't seen yet. And interestingly, that extra functionality is actually possible to do at, well, absolutely minimal cost overhead. It's so small that it basically doesn't matter. And it provides a backstop functionality to your deep network. Not one that you need to be super, super proud about, right? It's just a very basic thing. Just make sure that if you go far away from the training data, you'll get like 1 over C confidence. Okay, fine, right? But it's maybe something you just want as sort of standard functionality in your classifier. We used to have all these fancy pictures about adversarial examples for cars and self-driving cars and so on, where you just hold up some like QR code-like thing, and then the car thinks it's has to turn right or something, right? These simple adversarial attacks, and these kind of problems can be addressed with fixes like this, in a very simple fashion. Sometimes simple is good, I would say. Okay, so that was a detailed example. The other ones will be faster. Now it's also 11:05. Are there any immediate questions? If not, let's take a 5-minute break. So, okay, so I've shamelessly plugged some of our own work in this example, which I primarily use as a didactic motivation for why you want to be uncertain. Now I'm going to highlight some work by some other people, who is not us, now there's basically a string of work that all boils down to, and it's partly from my group, partly from other groups. There's a whole set of people in the world now, for example, at DeepMind in London, and in Japan, in MPS Khan's lab, and at Google in California, and in various other places at the ETH, that have taken this idea of a Laplace approximation and just run with it. So basically taken this insight that you can turn every deep neural network into a Gaussian process, and then just say, well, shouldn't that mean that all the functionality we are used to from Gaussian processes should now also be possible to apply to deep neural networks? And the answer typically is, yeah, sort of, actually, kind of works. So here's a paper, there's a lot of math, sorry about this, but I'm going to show you the high-level idea, by Alex Immer, who was at that time a PhD student at the ETH in Zurich, in Gunnar Rätsch's lab, who said, well, one thing you can do with Gaussian processes is using the evidence framework, so type 2 maximum likelihood, to fit hyperparameters. We did this in the example with the Keeling curve for Gaussian processes, right? You compute this log evidence, which is like this object, so the marginal over the model parameters, so integrating out theta effectively in a parametric model, which is possible in closed form for a Gaussian posterior, to get a quantity that depends on some hyperparameters theta of the model, and then we can tune these hyperparameters by optimization. So if we do this for Laplace approximations, then how would this work? Well, we again assume that our network is approximately a linear function of the parameters when centered on the trained neural network, which gives us, and additionally, we do a Laplace approximation on the parameters. So we do some kind of curvature estimate on the parameters using some matrix theta. Then this is an integral of a Gaussian approximate posterior on the parameters against an approximately linear transformation of those parameters. So that's another one of these Gaussian integrals, which just gives us a closed form expression that says the probability for the data, the training data, under this model is given by a Gaussian around the trained neural network with a covariance that is not just given by the likelihood covariance, not just given by this L2 loss, but additionally this kind of explanatory like kernel term that takes into account what the network learns from the training data, what the features are that the model uses to explain the training data. And now that's a quantity that you can take the logarithm of, so you'll get an expression that looks like this sort of term that we encountered in Gaussian process regression as well. There's on the one hand a data fit term that basically measures how close the predictions are to the training data when measured on a scale given by the feature covariances. And then a Occam's razor term, the log determinant of this matrix, where you can see that this is a scalar plus outer product term, so we can use some cool matrix determinant lemma tricks to compute this quantity and take the derivative with respect to some parameter eta of the model. Which parameters might those be? So they might, for example, be the parameters that determine the scale of the empirical risk compared to the regularizer, or maybe even initialization parameters for the deep neural network. And they did this kind of analysis in 2023, which was published in ICML, and it contains plots like this, which are taken directly from the paper, which I've linked up here, where they compare the marginal log likelihood against test accuracy for different kinds of problems. So here you see sort of typical standard benchmarks for very simple classification problems, CFAR 10, CFAR 100, fashion MNIST. And what you're supposed to see in these pictures is that, so this is the quantity that is being computed as a model evidence, marginal likelihood. So over here, the model is claimed to be has high probability for the data, and here the model has low probability for the data. And on the other hand, they're plotting test accuracy, which you can construct on a held out data set. And what you're supposed to see is that these are basically diagonal lines, right? So there's a strong correlation between the marginal log likelihood and this test accuracy, with the exception of this data set where it's not quite so good. And here you see in the color of these dots that this seems to have something to do with the size of the model. So if you get very small models, then sometimes this explanatory power of this model, of this framework breaks apart. But in general, for relatively large models, it's a bit more reliable as a kind of almost like a scaling law, right, in test accuracy. And then they show that you can actually compute this marginal log likelihood at runtime, at training time, and follow the gradient while you train the network. So at the original training, in a streaming process, you get sort of, these are two different runs, I think, this one and this one, where the optimizer continuously figures out how to set the relative size of the regularizer against the loss function, and it then ends up in a very good point during training when compared to the final loss function. So this is the black line in the background. Basically, you can use the Gaussian process metaphor to train parameters of the model during training, not post hoc, which is nice because a large part of finding good parameters for deep neural networks still involves trial and error. You just run the same training procedure several times in some, maybe in some kind of freeze, thaw, start, restart process. When you do that, you can replace it by this kind of approximate Bayesian framework. Another thing, completely different story, but you can also do is try to impose meaningful priors on the parameters of a neural network. So we discovered, or I pointed out, that the typical training loss of a deep neural network contains some kind of empirical risk and then a regularizer, and that we can think of this regularizer as a sort of log prior, a log Gaussian prior to the training process. But typically, that log prior is set to something like this, which corresponds to a standard Gaussian on the parameter space. And that's maybe really not a good prior for the parameters. It doesn't mean anything. It's like putting a standard Gaussian prior on all the terms in a kernel for a Gaussian process model, which would also give a badly calibrated prior. We actually did this in some of the earlier lectures, right? But you saw that this can be a very bad prior. And also, typically, people don't actually think of the regularizer in their deep learning problem as a meaningful prior. They just think of it as something that keeps the weights from going completely crazy. But there are some applications where you want to use a meaningful prior, not just to help with training, but to ensure that the model can learn a good representation of a function even from a small number of training points. For example, in some scientific applications, you might have a small number of measurements, I don't know, 20, 50, 100. Maybe you've caught some birds and measured their weight and their plumage or something, or you have some buoys drifting in the ocean, and you'd like to find out what the stream, the currents in the ocean are. So you have like 25 measurements, and you want to make a good prediction. Then you want to have, in addition to this empirical knowledge from the training data, you also want to use mechanistic knowledge from your knowledge of physics, basically. So for example, you might have something like a Hamiltonian, so a function that is constant in time, that describes some form of conserved quantity, like an energy, and that you would like to put into your function class, right? You might want to say, I only want to learn vector fields that conserve mass. So how do you do that? Well, you would like to have a prior on the parameter space that says, I'm only constant along equipotential lines of this non-trivial function called the Hamiltonian. And those are typically statements that are done in the function space rather than in the parameter space, because the parameterizations of the network are, they are down to a decision about architecture, right? How many layers the network has, what kind of nonlinearity they have. But the knowledge that you have tends to be in the F space, that the function has to have this property. So if you have a Gaussian process prior, you do that by choosing a kernel that is invariant under these symmetries. But for deep neural networks, at least before last Thursday, you don't have a kernel. Now that we have a kernel, we might impose such a restriction. So we might want to say that just like we had this reproducing kernel Hilbert space norm in implicit norm in a Gaussian process prior, we could also impose such a reproducing kernel Hilbert space norm on a deep neural network. And we would do that on the norm implied by this Laplace tangent kernel. It turns out it's possible to do that. It requires a little bit of fancy computation. So you need to find some representer points in the output space and then pull back the norm into the parameter space. How to do that, you can find in a paper written by Tristan Sancan, who is from the research group of Robert Bamler here in Tübingen, published, and Marvin Pförtner and other people, including Robert Bamler, published at NeurIPS just, last year. last December that points out that that's possible to do. And here's a picture from that paper. It's actually a data set like the one I just described. So here's the truth. Imagine you have some buoys drifting in an ocean. These are these little red arrows up here. So they're moving around. Each of these buoys has a GPS on board. It measures its drift. And you only have like, I don't know, 10 of them or so, a handful. And you'd like to use their drift to infer a vector field for the currents of the ocean. Now, we know that the amount of water is conserved. So this vector field has to be divergence-free. It must not have sources and sinks. Right? And that means that when you see a vortex, you can kind of close the vortex. Right? It has to, if something moves this direction, something else has to move this direction. And you can't impose this easily on a standard deep neural network. It's just not structured enough. You would need a regularizer on the function space represented by this neural network, not on the parameter space. And so Tristan and Marvin point out how to do that. You can do this with a Gaussian process, obviously, and then things sort of work. So here is the prediction, and these are uncertainty measures. This is the mean prediction from this training data. But that's expensive in the number of training points. It's also expensive in the domain that you're fitting over. And in fact, it's maybe even not a particularly great prediction. But if you wanted to do this with a deep neural network without some regularizer, then you get a nasty prediction that doesn't obey physics. But if you use a Laplace approximation on a deep neural network, so you're sort of doing deep learning, but you're also imposing this kernel regularizer, then you get a meaningful prediction. And these kind of models are now used actually for kind of scientific applications for this kind of like mechanistic knowledge to be included. One more example, final example, that I'm going to show you. Again, completely different story. First of all, is there any question about this or the previous thing? No. I thought so. One final thing is the answer to, or maybe not the answer, but like a partial answer to this point that I made about continuous learning, which again uses a fancy piece of math. It's basically just that's just there to, well, I mean, this is a research talk slide, so people just use math to intimidate and to point to things when there are questions. So I'm not going to say much about this math. But what you're supposed to see here, maybe you can see it, is expressions that you know from parametric regression or from time series models, from Bayesian filtering and smoothing. So imagine, actually I'll show you the picture. Imagine you have a set of training data that come in batches across time. So you first get the first set of training points. You want your network to learn on those. So in your head, if you want to have a simple example, think of MNIST, and I first show you all the 1s and 2s. And now you're supposed to learn what a 1 and a 2 looks like. Then we throw away the 1s and the 2s, and now in come the 3s and the 4s. And the model is supposed to learn the 3s and the 4s, but not forget about the 1s and the 2s. But we're not allowed to touch the 1s and the 2s anymore. They're gone now. They're in trash. So how would you do that traditionally? There isn't really a good way to do this in deep learning. Because if you're going to do gradient descent on this new training data, there is no way to guarantee that these new gradients on the new training points are not pointing in a direction that will destroy your performance on the old training data. So what people actually, well, I mean, I think the sort of the pedestrian solution is you just keep around the original training data and you loop over it again, which seems very wasteful. So instead, what you can do is something that has now been studied by several people, including by the research team of Kevin Murphy at Google, the guy who wrote the textbook, which they call LOFI, for low-rank filtering for training deep neural networks. And it works like this, and we've also worked a little bit on this, but it's a follow-up piece of work. So the credit is due to this paper by Zhang et al. In Kevin's group, which works as follows. So we're actually thinking of a Bayesian filtering and smoothing problem here. So we're imagining that we have a Markov chain of models going from left to right. And at time t minus 1, we get some data set at time t minus 1. We train our deep neural network on it. Now we have a posterior on the parameter space, on theta space, that is one of these Gaussian distributions in parameter space and associated Gaussian process in function space. And now the next, so now we can do some predict step, like a Kalman filter, basically. That predict step might be the trivial one. It doesn't change anything. It just says the future looks like the past. But it could be something else as well. It could follow some drift. It could say, the model seems to be moving in this direction. Let's continue this drift. And now there's a new training set coming in. And what we now do is we train this neural network, but we train not on the original regularized empirical risk problem, but on an updated regularized empirical risk problem. Do I have the picture here? Where the new implied covariance, this is this bit over here, this sigma t, it's not just, right, so sigma t corresponds to the regularizer in empirical risk minimization, the weighting for this L2 loss. We don't just get a scalar term, but we get a term that also takes into account that we've already seen data in the past, and that you somehow project, compress onto a compact data structure. So our regularizer is now going to be, instead of r of theta being equal to just theta star in L2 norm with maybe a constant in front, instead we're going to set it to theta transpose times epsilon 1 plus phi transpose inverse theta, where maybe with a psi inside, right? Something that takes into account the training data from the previous time step. And typically this data is then actually, so that's why it's called low rank, low phi in Kevin Murphy's parlance. It's actually somehow compressed using a singular value decomposition to some more compact representation. And this is, like, again, the details of the implementation don't matter. The important thing is that this is something that happens completely in covariance land rather than in point prediction land. Right? It's a functionality that you can only get if you have uncertainty. What this thing describes is a kind of sensitivity of the model to new data. It says, oh, which parameter of my network do you want to change? Oh, you want to change this one? You can't change that a lot because I've already seen some training data for this parameter. You're not allowed to change that. While this parameter, oh, I'm very happy to change that parameter because I haven't seen any information about it yet. Right? So if you think of your MNIST example, maybe you've seen the ones and the twos. So the ones all look a little bit like this. So in the middle of the pictures, the model is now quite confident about the classifier. And if I now come along with a 3, right, then it says, oh, the bits over here, I'm happy to learn about, but the bits over there, I'm not allowed, I can't do much about because I need them for the ones already. Right? And the data structure to store this in is exactly this matrix. In fact, MTS Khan now uses these visualizations, makes visualizations of these, I have pictures here, of these posterior covariances to show that, and talks about them as a kind of memory map for deep neural networks that you can use. They look a little bit like a CPU, right? Like representations of what the network learns about its own parameters as we get more and more data. So here we start task 1. These are the eigenvalues of the curvature matrix of the loss. Initially, they are all very low eigenvalues, right? Low curvature. The model is very unconfident. And then as we get one task after the other, you can sort of see the network filling in individual parts of its parameter space with knowledge. And those then get clamped down, basically. We say we can't change those anymore. And the network also gets more and more confident. So the eigenvalues go up, curvature gets higher and higher, and the network gets ever more confident about its predictions. Here's a picture from the, from the sort of follow-up paper from Joanna Sliva, who also used this framework literally in this Bayesian filtering and smoothing kind of perspective on one particular set of tasks. So I need to explain what these plots are about. They're from the paper that's linked up here. Here we go through tasks from 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 in each case. And what you see here in these brownish plots in the back are accuracies that one particular network has. It's always the same network in each of these plots on individual subtasks. So, example, that's not actually the application being used here, but in your head you can think again of MNIST, right? With you first get the ones, that's task number 1, and initially you train, you get, I don't know, 95% accuracy on classification for the ones. Now you throw away the ones, in comes the twos, and now you train on only the twos. And what you can see is that here, this brownish line says your performance on the twos is now also going to be 95%, but the price for that is that your performance on the ones has gone down. That's this line down here. And as you keep training, the performance will drop further and further on each of these old classes that you now don't see anymore during training. That's this, what's sometimes called catastrophic forgetting in continuous learning. And in each new data point that you get, right, of course, we get high performance again on this new subtask, but the old tasks get forgotten. If we now instead use this low-rank regularizer, so basically treat the neural network or treat the parameter space of the neural network as a time series on which we're running a Kalman filter, then you get this blue line over here, actually, sorry, it's this picture, or this one, depending on which of the approximations you use. And so the blue line in each plot is the average performance on all of the tasks. So there's always a new task coming in that you're good at, but you start forgetting the old tasks. And what you now see over these plots is that these old tasks tend to get forgotten later, right? They sort of decay more slowly, and the network uses degrees of freedom, capacity left in the memory that isn't used yet for the old tasks to continue performing. Overall, you sort of get, the line goes up, right, or stays up for longer. And now you can even do a funny thing where you also do a smoother. So you remember Kalman filtering and smoothing. The filter is the forward pass, the smoother is the backward pass. So you can use future data to try and learn about the old data. So I show you first the ones, then we throw away all the training data that is ones in MNIST, then all the twos, all the threes, all the fours. And afterwards, I ask you again to predict the ones. So if we just train naively, the ones will be forgotten, right? If you use a Kalman filter, the model will have tried to remember the ones. But what we can now do additionally is we can do this backward pass using the smoother, which are these update equations that you can look up in the lecture on Kalman filtering and smoothing, which will provide some information about these other classes that effectively comes from the negative information from the later classes. Right? So if I see a 2, I'm also learning what a 1 doesn't look like, vaguely speaking. And that leads occasionally, depending on the data set, actually to a further improvement on performance. So this blue line here is what you get if you run the smoother backwards through time compared to the filtering performance on each task. So the blue line is above the brown line, which is supposed to say you actually get better at predicting the earlier tasks from the later tasks if you move information backwards. I realized that was a difficult story. Ooh, any questions about this? Yes? So you're raising a point that is sometimes discussed in this parameter-efficient fine-tuning literature. Right? There's these sort of LoRa versus retraining plots that we will observe, I think, empirically often that there is a trade-off between the performance you get on new training data, on the stuff you want to fine-tune on, and the associated drop in performance on old data. So then you might argue, let's say, if you're thinking in the context of a foundation model, something like an LLM or a generative model for images that you want to fine-tune on some data set, that depending on the application, you might want to sacrifice some performance on the new data to keep performance good on the foundational task. Or maybe the other way around, actually, depending on what you want to do, right? Maybe you just want to be good at generating one specific set of images and you don't care about losing all the other stuff. So here, so my knee-jerk reaction to this question, now that you're asking, is that you actually have a knob here to twist to control this trade-off. And it basically comes down to, let me show this picture again, to very fundamentally to the Markov chain model that we're using here. So if you mentally go back, you almost do like exam revision, right, to the Bayesian filtering and smoothing lecture, you'll remember that Markov chains are described by two, they're sometimes called kernels, but that's a misleading term, by two probability distributions, one conditional distributions, one for P of theta t given theta t minus 1, so they explain how the time steps relate to each other, and one so-called emission model or observation model for the likelihood of the data given theta. So the relative size of these, if you think of a Gaussian approximately, controls how much you're forgetting the old stuff and how much you're learning from the new stuff. You could, if you think of this notation, so in Kalman filters we tend to have a Q matrix here, there it is, to make the prediction, and an R matrix, that's here called C because the plot's from the paper, for the observation likelihood. If you think of each of these as a diagonal matrix, here and there, then the scalars in front of, as a scalar matrix, then the scalars in front, the relative size of these controls how much you learn from the new data versus how much you forget from the old data. If you make Q close to 0, and you're saying nothing is changing, I have to remember everything from the past. And if you set R to 0, then you're saying the new data is absolutely important and I need to know the new data. So, right, maybe you want your model to only learn the new stuff at the cost of overwriting the old stuff, and maybe you want to keep the old stuff in. And that really fits into this mental picture of a memory map that MTS Khan is now pushing, right? In like traditional classic computers, we're used to having memory that has a discrete state that you can overwrite or not overwrite, right? You can say, I have some stuff, some memory set apart in my RAM or on my disk that I can write more stuff on, and when it's full, it's full. And I can decide to delete something. Now with neural networks, with deep networks, the story is more complicated because we have a soft kind of memory that lies in this sort of approximately linear space described by its local curvature, where you can say, I'm happy to unlearn a few things at the cost of putting in some new stuff, but it's still a high-dimensional space, so I might want to decide where to use degrees of freedom first to not destroy performance. That's a question.
So if you wanted to get as little as possible, would you just scale up the network to have like more redundancy in the weights?
Yes, so of course one possible answer is always let's just have more and more and more weights. Let's make the network wider, and then you just have more capacity. But that's like analogous to saying I can always make my computer more powerful by buying more RAM, right? And then or more hard drive or so, and then I can store more. But maybe I want to make a most efficient use of the memory that I have by, sort of defragmenting the memory, kind of pushing stuff into directions that I actually want. Maybe another mental picture is again this, in terms of this very simple two moons example is. So underneath here, there is a VLU classifier, right? So there's a bunch of VLUs lying here that you don't see in this picture. There's hundreds of them, actually. I think it might even be thousands. No, it's hundreds, pointing in like different directions. So if let's say you first see the blue data points, and then you know that later on there'll be these orange ones, then sort of mentally what we'd like to say is, oh, if there's a VLU that's sort of lying along this direction and pointing in this direction, I might want to use that first because it won't be affected by the orange stuff later on. Right? So I want to push knowledge into that memory feature. And that's exactly what this filtering and smoothing step can do for you. It provides a gradient that tells you which part of your memory to use to store the information in. For parametric models, we did exactly that in the early lectures. And there it's just linear algebra because all the computations are just linear. And now they've become nonlinear, locally linearized. And we're sort of iteratively trying to do this kind of process. Does that help? So the technical story has now become much more complicated than what we encountered in the case of linear parametric models. The computations are harder, they involve optimization, more complex curvature computations. But the conceptual value of probabilistic notions is still the same. The posterior covariance of a model provides a sensitivity map. It tells you what you know and don't know, or where you know more and where you know less, the relative information content of data and parameters, and allows you to trade them off against each other. So with that, I want to just highlight some papers, and then I show you the final slide. So if you want to know more, I realized that it was obviously a bit of a wild ride. It was mostly like an advertising tour for Bayesian deep learning in general and Laplace approximations in particular. There's various papers you can read, all linked here. You can click on all of these. For example, there are these libraries now that do Laplace approximations and more generally provide access in PyTorch to various curvature operations like Jacobian vector products or curvature vector products. There is a nice position paper by Felix Stangl and others on why such operations should be available in deep learning libraries. And there's also various papers that I cited during the talk, and some additional ones that if you like so maybe two things to highlight. One is if you like a differential geometry perspective, which I didn't have time to go into today, there is a paper here, the second to last one, which highlights the fact that this generalized Gauss-Newton matrix, this psi, this red object that I introduced a few times, spans the tangent plane on the loss manifold of a deep neural network, and that provides a deep, interesting insight into the geometry of these networks. That's actually an emerging field that people are now studying more and more because neural networks are parameterized function spaces, and those parameterizations are often actually quite questionable. They, for example, parameterize in a way such that that different values of parameters might correspond to the exact same network. So there might be invariances in the parameter space relative to the function space. That's a problem. It's a problem for uncertainty quantification, but also an interesting question for training dynamics. And there's now more people working in this direction, beginning to be interested in this. So here's a starting paper for this, and then you can do a forward search, people citing this. The other direction that's also, I think, quite interesting is the, let's say, political aspect. I used to have a slide for this, but then I cut it out, which you can maybe find some first arguments in this position paper on curve Lynops at ICML. Namely, that if you think about what we currently describe as an open model, if you think about LLMs, there are these debates about whether it's there are some companies that release LLMs, like Meta releases the Llama models, but they always only release the weights, not the training data set. So, I mean, they have good arguments for why they do that. They say, I can't actually release the data set, it's too large, and also it's confidential and has all sorts of legal issues, we can't release the data. But there's an interesting question of whether a model can really be considered open if you're just releasing the weights. And I think that this Laplace perspective is quite helpful for this thought process. Let me go to a corresponding slide, the very first one. So if you're releasing an open model, quote unquote, then you by releasing the weights of the network and the architecture, you're just releasing the blue bit, right? The point estimate. You're just saying, I've trained this network, theta star is the following value. And by calling my Python code, you'll get f of theta star. That's my model. And then what you can do with those released, so quote-unquote, open models is really just what you can do with that point estimate. If you want to do the other things that are highlighted today, like, for example, uncertainty quantification, fine-tuning, efficient fine-tuning without losing performance of the network, you also want to have access to a data structure that effectively approximates this object, this kernel. And you could ask companies like Meta or Black Forest Labs or whatever else you want to blame, right, for releases of a truly open model that also gives access to an approximate kernel, some data structure that approximates this. You could, for example, do this by constructing an approximate Laplace approximation in parameter space, compressing it down into a low-rank representation, some approximate singular value decomposition, and then releasing that as an extra data structure. And then that could be used for fine-tuning, for example, at higher performance. And it's not something that's currently done, but it's maybe a debate that should be had. You could also use that to approximately probe the data set, to check what the network actually knows and what it doesn't know, calibrate uncertainty, and so on and so on. So what I highlighted today is, well, I'm not going to read all of this out again, is that this probabilistic functionality that I introduced in the lecture on Thursday is not just aesthetically pleasing because it provides error bars on parameters and on corresponding function values, but because it endows, like uncertainty generally does, additional functionality into the model. It allows, for example, meaningful calibration of uncertainty, for example, to detect out-of-distribution data. There's also work that I didn't get to talk about for fine-tuning uncertainty within the training data region. That uncertainty can also be used to fine-tune the parameters of the model during training, just like we do for Gaussian process models. And it creates functionality like, for example, this fine-tuning across time for data sets that arrive after the foundation model has been trained. And in an age of increasing use of foundation models, so someone investing a lot of money into training a big model and then releasing that model to allow people to do interesting, cheaper stuff later on downstream, I believe that that conceptual functionality, uncertainty on the predictions of the network, will become crucial. How exactly we construct that function, this uncertainty, is up to research debate. I've obviously plugged some of the stuff that comes from my little subcommunity, Laplace approximations, which are primarily focused on low cost over quality. There are other people who argue more for quality and don't care so much about cost. That will be an ongoing debate. But the differences between these different approaches are minor. They are all just about how you do the computation. What we need to agree on is the industry standard for the data structures that go out. And that hasn't been done yet. And my argument is that it should probably be some low-rank matrix decomposition, structured low-rank matrix decomposition. With that, I'm done for today, and I'm also done for deep learning. On Thursday, we will switch to yet another storyline in the probabilistic history, namely random numbers. And I'm going to argue that there are no random numbers and that they are useless. We'll see how far we get with that. Thank you very much. See you on Thursday.